It's Ryan Soklaski here. I'm very excited to welcome you to the 5th year of CogWorks. We have a lot of exciting things in store for you, from processing audio data to making sense of visual data through the computer, and even quantifying language. We're going to be working together to create some very exciting projects and ultimately craft cognitive technologies that we're going to be presenting together at the end of this year. Hello, everyone. Welcome to the live session for the CogWorks final presentations. We're so excited to be sharing with you all of the exciting work that we've been collaborating on over the past week. We have 6 teams who attended the main CogWorks course, all of whom will be presenting to you their projects. And then we also have an international team from Mexico, and we're very excited to show their work as well. So without further ado, I would like to start off by introducing our team, Cog It Like You Mean It, led by the TA Jacob.
Hello, everyone. We are Team Cog It Like You Mean It, and my name is Catherine Lee.
My name is Darshini Anand.
My name is Hyojay Park.
My name is Joseph.
And I'm their TA, Jacob.
We wanted to help students in their day-to-day activities, hobbies, and chores by creating artificial intelligence programs that can work with audio, images, and text. Our first project is CogWorks, which helps students answer prompts that have images. Our second project is CogGreen, which helps students sort their trash. Our final project is Cogify, which helps students generate music.
First off, we created a program called CogWorks that can generate full textual responses to prompts that require the context of an image, such as a test question that asks the students to explain what a historical image might mean.
Our program works by taking advantage of pre-existing AI models and tools to simplify the work needed. This complete pipeline works to answer questions with images, such as an AP US History FRQ prompt, using a large captured segment of the internet as a source of data for learning.
We set out with the goal of providing GPT-3, an advanced language model with semantic understanding of an image. In order to describe the provided image and gather relevant context, we leveraged the Google Image API in order to make the best guess at what the image is. The Google Image API looks at a massive image database and tries to identify similar images. It then uses these similar images to obtain headlines for these results. We also leverage a headless browser in order to perform a reverse image search to find additional headlines.
We also make use of Google Vision, a computer vision model made by Google, in order to label particular objects in the image and perform optical character recognition, which looks for text in the image. These labels and the transcription of the text in the image are combined with the acquired headlines in order to provide image context.
We then use this context in the question to prompt GPT with the hopes that the context provides GPT with a semantic understanding of the image. GPT-3 stands for Generative Pre-trained Transformer 3. It is an autoregressive language model, a type of model that predicts a future word or token based on the tokens given in context previously. The GPT-3 model in particular was mostly trained on a publicly available dataset called Common Crawl. With this, GPT-3 can create anything that consists of some form of language structure. Its generative ability combined with its large knowledge base makes it the best option for our problem.
Here is a program outline of that entire process. To summarize, our image is converted into a description with the help of reverse image searching, Google Image API, and Google Vision AI. We then give the description and the original question into GPT-3 to get our final answer.
Finally, here are some of the results from CogWorks. Here we created a React web application where you can insert any image and a question related to the image. When you press Ask, it'll query our Express server, which will generate an essay or answer the question using the pipeline described before. At the end of the presentation, we'll show the link of the web application so you can try asking some questions yourself.
Next, we created a program called CogGreen that helps people with distinguishing waste as trash, paper recycling, or other recycling. Recycling is important, and this program will help you do it right.
Our first motivation for making this program is because many people don't recycle since they don't know how to or it's too much work. Since it's very harmful to our environment, especially with climate change becoming a bigger problem today. The second motivation is that some people try to recycle, but they do it incorrectly, which is actually worse than not recycling at all. Lastly, this program can help others learn how to recycle.
The data we used was from a project named TrashNet. This data set contains thousands of images of glass, paper, cardboard, plastic, and metal, each with a size of 512 by 384 pixels. We categorize paper and cardboard images as paper recycling, and glass and plastic and metal images as other recycling.
Some limitations and problems we initially ran into were mainly because of the size of our data set. For instance, we had to use MemMap, which allowed us to store our data on our disk and work with batches of data in memory at a time. We also had a hard time transferring large files, so we used OneDrive to store our files. We also had to change the way we train our model by loading batches of data into memory at a time.
When we finished preparing our data, we made a model that consisted of 2 convolutional layers and 2 dense layers. A convolutional neural network is a type of neural network that is often used for visual data. It consists of many filters that go around images looking for certain features, and these filters can learn to detect specific features like hair, color, facial features, and many more. These filters constitute one layer of a convolutional neural network. And by using several of these layers, CNNs can learn to interpret visual data very well.
After training our data for 10 epochs, we achieved a 74% test accuracy, 84% train accuracy, and a loss of 0.4. In the picture on the right, we see that a glass bottle was correctly predicted to be other recycling, which is metal, glass, or plastic.
And finally, we created a program called Cogify that helps people create music.
We wanted to create a neural network that could generate music all by itself, so we looked online for help. We found a blog that provided a model and a dataset of piano music from old video games. We prepared this dataset for our neural network by using Music21, which is a Python library for music. We were able to turn the song files into individual notes and chords, as you can see on the left.
We had a few main challenges when we were designing our model. Since we were using a different library than the ones used online, we had to closely look at the documentation to implement our own version. Another challenge was finding a data set large enough to ensure our model wasn't memorizing the music, but still able to generalize on broader patterns. Lastly, our initial model did not train on rhythm, so we had to change our methods of pre-processing to account for this.
For our neural network, our layers consisted of 2 LSTM layers followed by a dense layer. This type of neural network layer is able to use context to make a prediction, which is preferable when working with sequential data, such as music and text. We trained our data using this model, and we were able to achieve a loss of around 0.742.
LSTMs, which stands for Long Short-Term Memory, is a type of recurrent neural network that is exceptional at retaining information. LSTMs work by taking in input data and memory from previous LSTM blocks and outputs 2 things: a result and its memory that is then used by subsequent LSTM blocks to create sort of like a chain of LSTMs.
And here's a sample result from the model that was trained on video game music. Although it isn't the best music or the music you would hear on the radio, you can tell that the model is definitely picking up some patterns and nuances in its music. We also converted this music into piano sheet music, as you can see on the slide. Some ways that we can improve our project are to use more data.
Here are the references, and thank you for listening. We'd also like to thank our incredible instructors and TA for supporting us through these projects and helping us explore the field of machine learning. We also want to give a special shout out to Python Like You Mean It and CogWeb. Please let us know if you have any questions about our work.
All right, that was wonderful. Thank you, Team Cog It Like You Mean It. All right, next up, we have Team Ryan Sandwich, led by the TA, Sam. Take it away.
We are Ryan Sandwich, and we would love to introduce you to our project, CogShop, the AI-powered grocery assistant.
To start off with, we'll introduce our team. I'm Jamie.
I'm James.
I'm Laya.
I'm Tabeshi.
And I'm Henry.
And we also have our TAs,
I'm
Sam and Audrey, in this picture.
I'm Sam, the TA for the team.
So why did we build this particular assistant? Well, grocery shopping is a process that many people have to endure regularly. Automating at least part of this can save time and make shopping and meal planning less stressful. In addition, our design makes meal planning more accessible to those who may have busy schedules or difficulty finding recipes that suit their needs.
We'll begin by giving a brief summary of our program functions. As you can see here, we will be explaining each in detail as we go along with our presentation and share demo videos. To start off with, here are the data sets that we use for CogShop. We have an image-based grocery data set for image classification purposes, as well as text-based recipe and nutrition data sets for retrieving information.
Yeah, so starting off with our object detector model, in order to recognize food from an image, such as maybe a photo of groceries in our fridge or pantry, we first needed to be able to detect objects from the background of an image. To do this, we used a pre-trained object detection model from PyTorch called Faster RCNN Resonant 50, in order to return coordinates of detected objects for an inputted image. Faster RCNN is trained on or learns from a large image dataset called COCO, which provides the model with object coordinates for a specific image beforehand. Through learning how to reproduce the matching coordinates for a specific image from the database, the model is then able to learn how to return coordinates for a completely new image. Next slide. In the image on the left, which happens to be a picture of my fridge, you can see a demo of the object detector. And the object detector can also classify certain objects of food if they're in the COCO dataset, like the oranges or apples at the bottom of my fridge, or like cake. However, in the case that a detected object of an image isn't in the COCO dataset, it gets sent to the image classifier that my teammates James and Debeshi worked on.
To classify an object as a certain kind of food, we use a strategy called transfer learning, in which we use a pre-trained model that is already adept at recognizing patterns and train it even further on our data to get results more efficiently. We use the model Resonant 18, which was trained on an image dataset called ImageNet, and we trained it further using our grocery dataset. The image classifier takes in the coordinates from the object detector model and determines if the object is a type of grocery item.
How does Resonant 18 work? Resonant 18 is an 18-layer convolutional neural network, which is a type of neural network that excels at recognizing features and patterns in an image. Using transfer learning, we train Resonant to identify features and images of our dataset. These features were then passed into our dense layers, which were trained to classify an image based on its features. Here are some examples of this model in action. You can feed in an image of an object from various angles and lighting conditions, and the model will be able to classify which type of grocery item it is.
For our speech-to-text application, we used Python's included speech recognition library. We use this to generate a transcript from our voice that recognizes keywords specific to food. We could then use our transcript to search for recipes or create a hands-free shopping list.
So to go into some strategies that we can use with these models and techniques, first, to find the nutrition of food from an image, we took in a list of the food items discovered in an image by our models. We then used speech recognition to have the user decide what food item they wanted to analyze, and then search the nutrition data set for its information accordingly. The process for finding recipes was similar, except instead our function took in a speech-to-text list of ingredients and then searched the recipe data set for recipes that most closely match these ingredients. And we can show a demo video of retrieving nutrition here.
Nutrition. I can now insert a file path to any image that I would like to check nutrition facts for. The image will then be sent to object identification to identify each individual grocery item in the image. After it identifies each object in the photo, it asks me which specific object I would like the nutrition facts for.
Here we have our recipe retrieval system in action.
Find recipes. Chocolate, vanilla, strawberry. Yes. As you can see, it generates a recipe containing chocolate, vanilla, and strawberry.
Our next function, our shopping list function, informs users what groceries they still need to buy by checking the contents of a pantry or fridge against a shopping list. To accomplish this, our models identify the groceries found in an image, checks them against a shopping list taken from the user using speech to text, and then prints out what items are missing.
Here's our shopping list demo.
Now let's use the same picture of the fridge to identify objects in the fridge and compare them to a shopping list to see what we're still missing. Shopping list. Again, the image is passed through object identification to identify each specific object in the photo. Milk, apple, pasta. Yes. Using voice recognition, I generate a shopping list, and the CogShop will return what's missing in my fridge.
Now, normal old recipes do well most of the time, but what if a user is looking for something more creative? CogShop has just the thing, recipe generation. To do this, we use something called an n-gram model that finds patterns in how text appears and the probabilities of certain words appearing after others. We trained this model using our recipe dataset. By using the probabilities and patterns found from this dataset, we created a function that could generate a completely random and sometimes nonsensical recipe. Here it is in action.
Generate a joke recipe. Here, it generates a random recipe using text generation.
We experienced some problems when classifying foods. Our accuracy, while far better than randomly guessing, was about 54% for new data. This may have occurred because we only had 200 images per class in our grocery dataset. The fact that our dataset was also composed of German products might have also been a problem.
The object detector model also had a few drawbacks, primarily due to the datasets it was trained on. As you can see for the image on the left, the model has trouble detecting all the objects in the crowded space. This is likely due to the fact that most datasets like Coco, which the model was trained on, have images where the objects are distinct and all spread out. If we were to make improvements to the model, we would use data where the objects are close together. The picture on the right shows a model that was trained using a dataset called SKU110K, whose objects are close together. And as you can see, the performance is drastically improved.
And finally, we would like to finish off by giving a huge thank you to CogWorks for teaching us and for making this project possible.
All right, thank you so much, Team Ryan Sandwich. Folks, I'll tell you what the sandwich is. It's peanut butter, pickle, and honey. Don't knock it until you try it. I'm telling you, it's good stuff. All right, so next we have the team Oh My Gauss. Team Oh My Gauss, please welcome. Oh yeah, there you go. All right.
Hi, Oh My Gauss here. My name is Ozan.
I'm Sophia.
I'm William. Leon.
I'm Koa.
And I'm Clarice. Okay, so to kick it off, within our final capstone, we decided to pursue 3 different projects, each inspired by a CogWorks week, but still all within the theme of music. For the audio module, we have music synthesis and note detection. For the language module, we have sentiment analysis on lyrics. And then for the visual module, we have sheet music reading.
So you may ask yourself, music synthesis with note detection? What? My goal behind this project was to extract clean, coherent strings of notes from WAV or MP3 files, then use these notes to train a model to synthesize music one note or rest at a time. My intention behind this was to bridge my interest in spontaneous music improvisation and computer programming. I play a lot of guitar, so I thought it'd be fun to teach a computer to make music similarly to how I do. But first, some background information within the domain of note detection. For those unfamiliar, this is a spectrogram. A spectrogram is a visual representation of the spectrum of frequencies of a signal as it varies over time. It works by decomposing the signal into frequencies and their respective amplitudes by taking discrete Fourier transforms at every given time step. My approach to note detection is premised around spectrograms, as they allow me to search through the list of frequencies and amplitudes for the fundamental notes that I want to retrieve. Overtones are musical tones which are part of the harmonic series above a foundational note. Often, when a single note is played, there are numerous other higher frequencies that resonate along with it, which make up the overtone or harmonic series. To the right, you can see the spectrogram of Never Gonna Give You Up by Rick Astley. In this, the only notes that are actually being played occur near the bottom, as you can see, indicated by a more saturated shade of yellow. The remainder of the frequencies shown are overtones. As depicted, it is possible for these overtones to have comparable amplitudes to the foundational played notes. This brings up a fundamental challenge in this note detection. In order to retrieve the notes that were played, one will have to weave out overtones and other possible frequencies, which may be more readily visible than the fundamental notes. In computer-generated music, this is less of a problem, so I implemented the procedure as I normally would. First, I converted the audio to digital samples. Then I passed my digital samples through a spectrogram. Then I identified the frequencies with the highest amplitude per time step. Following this, I identified frequencies that persisted throughout multiple time steps. And finally, I converted these frequencies and timestamps into a note object that I had predefined. Here is the process being done on the Mi Plaza theme. As you can see, the program is able to derive the notes from the original signal. However, natural sounds contain many overtones. I approached this issue with three solutions. First, I took the moving average of the raw data signal, which smoothed out some of the roughness from the recording. Then I implemented algorithms which would search for undertones below a located frequency, in case the frequency that the program had detected was, as a note, was itself an overtone. I also implemented further methods to remove erratic jumps in the recovered signal, which occurred due to imperfections within the original sample. Here is an example with a guitar clip. For cleaning, you can see that the frequencies fluctuate pretty excessively, and it's pretty clear that the notes are not a very good representation of the original sample. After cleaning, the notes visually appear much more consistent with the original signal. Accordingly, the audio is pretty similar to the original data. Armed with data, it's modeling time. An n-gram model is a model that operates by generating an nth item given a history of n-1 items. It does this by randomly selecting an item using the probabilities of each subsequent item, which are determined through analysis of a large body of data. Models like these are commonly used in natural language processing, but are also applicable to music due to its sequential nature. Sophia and Clarice wrote the code for this model. Thanks, Sophia and Clarice. I trained it by recording my own guitar improvisations, deriving the notes from the recordings, computing the intervals between notes and semitones, and passing these semitone intervals into the model so that it generates notes as intervals. This way, the model is not bogged down by discrepancies in key within the training data. I ended up using a 12-gram model. Here's what it made.
So the next project is lyrical sentiment analysis, and the goal of this project was to classify a song by having a positive or negative sentiment based on its lyrics. And we used a data set of 1,000 songs from many different genres, and each of the songs were labeled as happy or sad.
In order for the computer to classify each song, we need to encode the lyrics using TF-IDF. TF-IDF will return an array of numbers that gives a numerical value to each word in our lyrics based on how important they are. The first part of 2 is to take the lyrics and create a list of vocab words, and from them we tokenize by filtering out stop words, white spaces, punctuations, and we lowercase everything. Then we take that vocab list that we just created and we sort by the top n words by occurrence. And lastly, we calculate the frequency of each word with the vocab list. For the next part of TF-IDF, we use the equation log 10 by n over nt of each word in our vocab list, where n is the number of songs and nt is the total number of documents in which term t appears. We decided to use k-nearest neighbors since it is a classification algorithm, and k-nearest neighbors just looks at a certain number of nearest data points and finds the distance between them in relation to the query. We use the TF-IDF array to find the cosine distances by normalizing our test and training data and then transposing the said training data to find, then using the dot product to find the distance between them and subtracting it all by 1. So in this picture in the top left is an example of how k-nearest neighbors works. The green data point is the point we want to classify, and if we were looking at the 3 nearest, we could see that there's 2 blues and an orange. So we will classify that green data point as a blue. And we got around 72% accuracy with our model, which isn't that great, but it's better than randomly guessing.
Our second method was using a dense neural network. So as you can see, you have an input size of 400, which is the length of a TF-IDF vector for a particular song. And we feed that into the input layer, and it goes through 2 hidden layers. And in between the hidden layers are updatable model parameters. And lastly, there's an output layer, which includes 2 nodes, basically 2 outputs that represent the negative sentiment score and the positive sentiment score. And the way we train this model is with cross entropy loss, and we also applied softmax in addition to the atom optimizer, which allows the model to have parameters that would better find patterns of the data. And the training results of this show that the model performs quite well on training data, which was 800 songs within the training batches. So it kept on seeing the training data and it updates its parameters accordingly. However, the model wasn't able to generalize super well on testing data. As you can see, the testing data, the testing accuracy was around 75 to 79%, which shows signs of overfitting. So the limitations of this project was that, so one of them was we only used a data set of only 1,000 lyrics. So that limited the model in terms of words and like a range of patterns and nuance. And in addition, the meaning within songs can be, it isn't always obvious because many songs would use metaphors as opposed to like obvious statements. For example, because I'm happy versus I'm a hot air balloon that could go to space. They're both positive, but it's not always obvious to the model. And lastly, sentiment can be quite subjective, and it doesn't always like go one way or another, as opposed to like something like restaurant reviews online.
The final part of our capstone project is reading sheet music using object detection. The motivation behind this project is to help music lovers hear what they're composing or playing. The task for our algorithm is to read notes on a page from left to right and play them out in the correct order, duration, and pitch.
So how did we approach this task? Well, we started off with some research and we found that current methods of sheet music reading employ purely algorithmic approaches such as template matching and semantic reconstruction. However, upon testing those approaches, we discovered their inaccuracies and inconsistencies. That brings me to our approach of 1, using blob detection as illustrated by the diagram on the right, 2, using a custom data set for training, 3, using 2 convolutional neural networks for classifying, and finally 4, a MIDI file generation method to play our detected notes.
So first, the blob detection. When we get a lot of music, the first thing our algorithm does is it tries to figure out where the notes are on the page. In order to find the notes, we use a Python function from the OpenCV library called blob detection. A blob is a group of connected pixels, such as the note heads of the notes. But in order to better emphasize the note heads and improve our overall accuracy, we first applied erosion filters to remove the noise on the image, such as the staff lines and bar lines. We also used a dilation filter in order to ensure that the half notes and whole notes, which more closely resemble empty circles, are also picked up by the blob detection. Finally, using the coordinates of the blobs or note heads, we crop around the entire note and return the results for the next step.
As mentioned earlier, we created our own custom dataset for this project, and to elaborate, this dataset includes 14 pitches ranging from C4 to A5, including the rest pitch of 0 frequency. It also includes durations of notes ranging from 16th notes to whole notes, and then also 6 locations of the note in an image. In total, that made our dataset have a size of 1,122 images. After acquiring our data, we pivoted to the data preparation stage in which we applied 2 approaches, padding and resizing, before feeding the images into our model.
So once we obtained the individual images of notes and rests from the blob detection, we used a convolutional neural network to classify both the duration of the notes as well as the name of the note. This image here on the slide is of a CNN used to identify images of vehicles, but the structure of our CNN is very similar. Convolutional neural networks are particularly useful for image classification, especially in our case where the note and staff in each image is never in the exact same position, because they utilize convolutions, which are a special type of layer that are useful in picking out important features in images through applying filters. Once we input our images into this model, it outputs a probability for each of the possible classifications, and we then take the highest probability as our final prediction.
Given that we have two models and each outputs an array of classifications, we needed some functionality that would map those arrays to the appropriate values when being played as a MIDI file. So unlike the MP3 files you're probably familiar with, MIDI files are an easy way to store sequences of audio data, which is perfect for our project. Using two functions, write music and play music, the arrays that the models output are passed through their respective MIDI conversion dictionaries, written into a MIDI file, and then played. Here's a demo of how this works.
Okay, moving on to the evaluation. After adjusting the parameters of our blob detection, we were able to consistently pick out all the notes except for the occasional half note, which is particularly difficult, shaped as a thin donut. Our classification models achieved a relatively good accuracy around 65 to 70%. However, the training data accuracy reached over 90% for both models, indicating that there's a sizable amount of error due to overfitting. We plan on improving this classification accuracy by training our model on a larger amount of data in the future, as well as trying data augmentation techniques such as randomly cropping, rotating, and adding jitter to our images.
And that wraps up our sheet music reading project. Considering we only had a week to do research and work, there are many improvements we can make, including what Sophia mentioned about data augmentation, but also for extensions of the project, we can implement more classification abilities, such as a larger pitch range, the ability to read clefs, key signatures, time signatures, dynamic symbols, staccato, slurs, and so on, and the ability to identify sound source from a variety of instruments. So while today marks the end of BWSI this summer, we're very excited to continue this project in the future.
Thanks for tuning into our presentation. Feel free to leave any questions you may have in the Q&A box. We'd also like to take a moment to thank our TAs, instructors, and BWSI staff for enabling this incredible educational experience. And if you like learning Python, you'll love Python like you mean it. Thank you.
All right, thank you so much, Team Oh My Gauss. And for the record, folks, I did not put them up to repping the website there, but can we also appreciate their wonderful background that they created with the water flowing through pipes and Gauss? Good stuff. Okay, next up we have a group of pandas led by their TA, Andrew.
Hi, we're team A Group of Pandas. I'm Akshita Tiwari.
I'm Kylan Williams.
I'm Michael Huang.
I'm Adriana Peng.
And I'm Joe Lin. Sorry.
Hi, no, I'm Andrew. I'm their TA.
Our first project, SILT, is a sign language interpreter and translator. Our project helps to facilitate a conversation between someone and another person who is hard of hearing or deaf. The software uses neural networks to recognize live sign language from a webcam. It is then able to detect these signs, transcribe them into text, and convert them into speech. It also conducts a conversation in reverse by interpreting the speech and converting it to sign language. This is presented to the hard of hearing user as a sequence of videos of sign language.
So what is a neural network? A neural network is essentially a programmer's attempt at writing or quantifying how humans learn. So the way a neural network works is it takes in an input, like an image, makes a prediction on what is in that image, and then uses what's called a loss function to determine how well that neural network can predict what's in that image. Then we use gradient descent to determine what parts of the network correspond to what parts of the output, and then iteratively optimize towards the predictions we want it to make.
Let me tell you about the pipeline for our project. First, the software detects signs the user is making with their hands through the webcam, and then translates these into corresponding sign language symbols. The signs are then recognized and transcribed into text, which is later converted into speech. Similarly, another option is to first have speech as an input, and then have the software convert it to text. The text is transcribed into sign language, which is then stitched into a single video and presented to the hard of hearing user.
The first step is detecting the hands in an image. To detect the hands in an image, we used a pre-trained neural network called MediaPipe. It was built by Google, and it draws points at each of the joints in someone's hand. We then give these landmarks to our neural network to figure out the sign that that person is trying to make. MediaPipe works in two main steps. First, it draws a box around the hand in an image, and then it places points at each joint in that image using what's called a single-shot detector. A single-shot detector draws boxes over the objects in an image and then resizes them depending on how well that box fits the object in the image.
All right, so now we got the input of the hand and the landmarks. So now let's show you how to detect signs based on that. Yes, play the video. So here is a video of me trying to spell the word hello. And I'm spelling each word very slowly because I don't know the language very well. And as you can see, we recognize each letter, each sign as a letter, and then we are able to concatenate them together using some filtering technique to stitch together the word hello. So basically, to recognize sign based on image and landmarks, we try two approaches. The first, a convolutional neural network approach, whereby we just pass in the image and try to process image and recognize a sign based on that. And the second approach we try is a densely connected neural network approach, where we pass in the landmarks, positions of the landmarks, and try to recognize a sign based on the locations of the landmarks. Eventually, we combine the two models to make our final prediction because we find that this increases the accuracy at test time. And so here is a diagram of the entire system of our silt detector. First, we obtained a crop image of the hand as well as the landmarks position. We transfer the landmark position to a polar representation to help facilitate the detection of the recognition of the sign. And then we pass it in through a densely connected neural network as shown on the right. And on the other hand, we also pass in the entire image through a convolutional neural network. And combining the feature generated from the crop image as well as the landmarks, we are able to generate our final sign prediction. Next slide, please. So a little bit about the convolutional neural network we use. Here's a diagram showing the convolutional neural network. The first step is a pre-trained MobileNet v3 model. And after that, we stitch together a couple of convolutional neural network blocks. And MobileNet v3 is basically a chain of what they call bottleneck blocks stitched together. Bottleneck blocks is just a fancy way of doing convolutions such that it saves memory. And basically, they're using depth-wise convolution and point-wise convolution as shown on the right-hand side to achieve similar result as a normal convolution while saving tremendous memory. We chose this model because it's very efficient and it can run on a web app very well.
Yeah, so in the process of converting sign to text and then to speech, so for the first part from sign to text, we're parsing the sign into the text and we're using the Google text-to-speech software. And this is an API powered by Google's machine learning technology. And the text-to-speech API converts the text into something called SSML or speech synthesis markup language, and it turns it into audio data using CNNs.
Onto the audio or text to sign portion, similar to converting text to speech. To convert speech to text, we utilize the speech recognition module that use Google's speech recognition API to translate audio input into words. So roughly how this works is that you start with an analog signal, which is, for example, your voice. And that gets converted into a digital signal through a microphone, and that gets passed into Google's model, which is a RNNT model or a recurrent neural network transducer model. And RNN models are good at processing sequential data because they maintain like a history of all of its like past inputs and results. But a RNN transducer model is particularly good for this purpose because it can process them in real time. The model analyzes distinctions, it predicts the text and outputs it.
Yeah, so going from text to sign language, so we use a very large American Sign Language database, and we basically query each word in our string of text. So we query the words from the database, and the database basically stores from word to video. So we're pulling each video corresponding to each word, and we're concatenating them using a Python library called MoviePy.
Our next project is called Roshan Bot. It's a rock, paper, scissors detection game. So Roshan Bot is a game that allows you to play rock, paper, scissors against the computer with your real hand. It uses a dense neural network and hand detection similar to our sign language detector or sign language translator. And the computer generates a rock, paper, or scissors to play against you.
So here's how the pipeline for Roshan Bot looks. The user is first prompted to generate a play, either rock, paper, scissors with their hand, which goes through our model, and the model detects it. So after that, the computer generates its own move randomly, and the score for each round is calculated based on the results. Here's a demo of our model. As you can see, if you can play it. Yep. If you pay attention to the terminal, that's the thing on the bottom outputting text, you can see that it works in real time, and it's like really flexible. It can recognize like the symbols rock, paper, scissors at various angles and various positions too. Yep. It's really low latency.
We also created a graphical user interface for this game using Pygame. At first, the user is directed to a start screen, which includes a help button, which leads to the instructions page with rules for the game. The start button directs the player to the live detection game. The instruction page basically provides the user with steps and details on the computer's plays, as well as information about the score. And on the game screen, the user is prompted to generate a shape of a symbol, either a rock, paper, scissors, with their own hand. This leads to the camera popping up, and through the webcam, the software detects the user's symbol. The computer's play is also revealed right after the detection and is used to calculate the score for the round. We also gave the user an option to play as many times as he or she would like.
Yep. Here's another demo, my hand again. Yeah. You can see me going through the interface right now. Here's the instructions page, as Akshata mentioned, and start. If you pay attention to the choices where it says you picked blah, agent picked blah, you can see the results for each round I play. All right, so some disclaimers. All of the people involved in this project do not regularly use sign language and were not very familiar with it beforehand. And this project was just meant as a general ASL to English translator. We understand that not all people who sign are deaf or hard of hearing, and not all people who are deaf or hard of hearing sign. So its purpose is not exclusively between those parties. A potential future application, or well, not future, but a potential application would be using this as a tool for people to learn sign language.
Yep, to throw in a couple of words for future works for the project. So as you can see, the project, we have a lot of directions to expand on. And one direction that we can expand on is that, as you can see during my demo, that currently we recognize each sign as a letter. Basically, we're only recognizing 26 signs corresponding to 26 letters. We're hoping to expand it to a word level translation from sign to English. So currently our letter recognition system achieved an accuracy of 98%, which is a little bit short of the 99% of the state of the art. And in the future, we hope definitely to make a word level translation. And word level translation is actually the state of the art of research at the moment, but we are definitely planning to do that. The other thing that we plan to do is to use an NLP model to stitch together a sequence of letters together into words. So currently we are just using a parser that basically parsed a sequence of letters recognized from the sign into a word. And in the future, we will try to make a more sophisticated sequence to sequence model. And Joe, do you want to speak on the?
Yeah. So another thing is, as you may recall, for our pipeline for text to sign, we pretty much just did a simple method for like querying to a large database. So instead, for one of our future works, we plan to implement some sort of transformer based network architecture so that we can better convert text to sign language. And we'll also be working on like perfecting the UI, which we unfortunately cannot show today because my screen share apparently doesn't work.
All right, thank you so much, group of pandas. Next up, we have Team WOW, led by the TA Darshan.
Hi everyone, I'm Chris Gu.
Shruti Sharma.
I'm Svanik Sharma.
I'm Evelyn Zhu.
I'm Darshan, the TA for the team.
Our team's project focused on music analysis with machine learning and deep learning algorithms. The analyses that we focused on were sentiment analysis, lyric generation, audio generation, and genre classification. We'll start off with sentiment analysis. Sentiment analysis is essentially the process of an algorithm, usually a machine learning model, determining the emotional facets of language. Now, this is difficult because language is subjective and not quantifiable. For our project, we decided to gather a database of our favorite songs and then divide them into two groups based on if they had a happy or sad theme to them. And the goal was to have our DL models correctly classify the songs into these two groups when only given their lyrics or their choruses. For the DNN, we used the IMDb Movie Review Sentiment Analysis dataset. There were 10,054 unique words seen across all reviews. The labels of the reviews were two-dimension, and all other statistics are posted. For pre-processing, we first counted the frequency of each word in the review and removed any stop words, which were words that didn't carry any significant meaning. Next, we converted those frequencies to TF-IDF values, which is a weighting mechanism to determine the importance of each word. Finally, we normalized those values. So for our model, the DNN had two layers without any activation functions. A representation of the model is shown on the right, and training statistics are listed on the left. Through our training, we end up with a strong validation accuracy towards the end, and there's a little bit of overfitting because the training curve minutely eclipses the testing curve. For results, the DNN achieved a decent accuracy when the song's choruses were used to classify. Through the confusion matrix, we can see that the classification was pretty even, and other classification metrics are listed as well.
The second model we created was a convolutional neural network, or a CNN. This model was trained on a publicly available Twitter dataset, which was pre-processed to keep everything clear and consistent. We also used glove embeddings, which essentially translates human understanding of language to machines. The reason we wanted to test out a CNN is because of the model's ability to learn how words grouped together can indicate a pattern. CNNs are usually used on computer vision problems, but we can also use them on language. In our case, we only have one dimension, which is time, so we use a 1D CNN. So listed here is the architecture of our model, as well as some hyperparameters. Something important to note is that we only have one output, which is a value between 0 and 1 to indicate the sentiment. And after training our model, we tested it out on our self-created dataset, and the results are depicted in this confusion matrix here. And overall, we achieved 74% test accuracy.
So RNNs, or recurrent neural networks, are DL models that are specifically designed to learn sequential data like language. Through the diagram below, you can see how the calculations are carried into future ones. But one major limitation of basic RNNs is that they have trouble remembering earlier inputs and later calculations as indicated for the nodes in red. The LSTM, or long short-term memory mechanism, corrects this drawback by adding additional complexity into each calculation of the model to keep earlier inputs and calculations accessible to later calculations. For the RNN, we use the same dataset, but with a fifth of all reviews dedicated to testing. And with pre-processing, we limited the word count of reviews and did a sequential integer word encoding base structure, which meant that each word was converted to an integer ID in the same sequence. The Y value this time was one-dimensional as shown. The RNN was composed of three components. The first layer was a trainable word embedding layer, which converted those integer word encodings into a vector. The second layer was the RNN itself. And then the third and final layer was just a dense layer. The training statistics are listed below as well. For training, while there was a high testing accuracy, the RNN experienced substantial overfitting because of the disparity between the training curves and the testing curves. And for the results, the RNN LSTM had the worst performance. The results show that more complex doesn't always mean better, but we do have to keep in mind the subjectiveness of sentiment analysis and the unusual dataset choices for this project.
Our second project focused on generating song lyrics. We approached this like a text generation problem, where our goal was to produce text that could resemble lyrics. The first model we trained on was an RNN LSTM, which you now know about. The results of this model on generating characters aren't too bad, since here we can see some actual English words being generated. We also went ahead and tried to generate lyrics using an n-gram model. What an n-gram model does is it predicts the probability of seeing the nth word based on a history of n-1 previous words. So we are basically trying to statistically create text based on how frequent certain sequences are. We trained the n-gram model on a corpus of lyrics from our self-created dataset. The output of the model is a dictionary, where the key is a word that corresponds to the distribution of possible words. Our n-gram model does a decent job actually of creating lyrics. With the 2-gram model, we can see there are certain phrases that do make sense. Now, one of the limitations which you might have noticed is that our model is highly dependent on the training corpus. With the 3-gram model, for instance, you can see that it actually starts to copy the exact lines of songs because our model was trained on such a small data set without enough variety. So to improve on this model, we would definitely want to train on a larger set of data.
And now we move on to audio generation. So the objective of this project was to generate music that sounds good to the human ear. When deciding what type of music to generate, we decided to use classical music, since it's more structured compared to contemporary genres like rock, pop, hip-hop, or metal. And the approach we used was similar to n-gram, in the sense that each note that was produced was based on the previous sequence of notes. The model that we used to learn this probabilistic distribution was the WaveNet model. It's a deep autoregressive model, which means that it can predict future values, such as note values, based on past values. The architecture of this model is pretty complicated, but it can be dissolved into 3 specific layers. The first layer that really matters in this model is the causal convolution layer, which is basically what makes the model autoregressive and is what allows the model to predict future note values based on past values, kind of like an RNN LSTM. The next layer that is very important for this model is the dilated convolution layer, which basically increases the receptive field of the model without actually increasing the kernel size. It also preserves the audio input resolution, so future layers can actually use the original, or they can basically use the audio as is from previous layers. The final layers that really matter for this model are the residual blocks and skip connections. They preserve information learned from other layers and pass it on to the layers up top. So that means that layers can learn from features that were extracted previously. They also stop the problem of vanishing gradients, which is basically when a neuron's activation is so low that the model basically stops learning altogether.
So in terms of experimenting, we tested the model using several different number of input nodes to generate a new note. And we found a correlation between that hyperparameter with the sophistication of the generated music. I'll now play some snippets of the music produced from the WaveNet model.
Our next audio technology is genre classification. Next slide, please. In this project, we used convolutional recurrent neural networks to predict the genre that most correlates with a song sample based on its spectrogram. For our project, we utilized GitSan, a dataset widely used for music genre classification. With GitSan, we were able to correlate WAV files of song clips to their genre labels. After pre-processing, we trained and tested our model with 10,000 song samples over 10 genres, 80% of the data used for training and 20% used for testing. While CNNs are majorly used for image classification, they can also be used for audio classification, as we can represent sound over time with a spectrogram and represent it as a vector or multi-dimensional array, since a spectrogram is a numerical representation of song frequencies occurring over time. When using this type of data, CNNs are very useful because representation of features in input data can be made regardless of where those features occur. Because our input data is sequential, as we have music notes over time, the input data was fed to an LSTM after going through 3 one-dimensional convolution layers so that both long and short structures among music genres could be identified. An LSTM was used because it can remember earlier sequences better than a basic RNN. After 100 iterations of training, our model produced a training accuracy of 48.2% and a validation accuracy of 46.6%. There are various reasons for this model's performance. Next slide, please.
So Shruti was saying there's a lot of reasons as to why the model didn't perform as well as we thought it would. One of the reasons is the dataset distribution. Here, I use principal component analysis to break down the audio features of each audio file from both of the datasets that we tried to use, and I plotted it in two-dimensional space. You can see that there's a lot of overlap between the genres. For example, you can see that blues music and jazz music tend to overlap a lot, and so do metal and rock. This intuitively makes sense because a lot of genres are generally just mixes of other genres, and a lot of songs that tend to combine elements from multiple genres. So after thinking about it, we actually did some last-minute research, and we found out that we can actually just use a deep neural network model and not any fancy convolutional or recurrent models. You might be asking, how is this possible? Well, key feature here that matters is that instead of using the raw audio or MEL spectrograms that we produced from the audio files, we actually used the audio features such as chroma, spectral bandwidth, and harmonic mean to produce a higher accuracy. So these features were actually available to us in the dataset, but we hadn't actually thought of using it for predicting the genre. We were just simply using the raw audio. So once we took these audio features that were extracted for us and normalized them, we then just simply used a couple layers of, or a couple of dense layers with dropout and batch normalization, and we obtained a much higher accuracy, as you'll see. The results of the deep neural network were extremely impressive. The training accuracy was 96.89%, and the validation was 93.35%. What this basically shows is that sometimes just using the raw audio or MEL spectrogram data, or really in any project, just using the raw data given to you, isn't always good. The lesson we learned was basically that you should always explore your data set, and that you should always try to extract features that are meaningful from your data set that are given to you if possible.
So in terms of future planning, we definitely could have expanded upon sentiment analysis by building and testing more machine learning models, using TF-IDF for our RNN LSTM model, and ensemble learning, which is combining the power of multiple models to create more powerful prediction methods.
Both sentiment analysis and lyrics generation, it would also be interesting for us to try using a transformer model or an attention mechanism for the RNN LSTM models.
For audio generation, we'd like to make our music less repetitive, and we'd also like to try other models like RNN LSTMs and GANs.
For genre classification, we are interested in researching the nuances in how music is classified and the different audio features that can be used to more accurately classify songs by genre. We would also like to research different classification techniques, such as k-nearest neighbors or k-means clustering. Next slide, please. Thank you for listening to our presentation, and we would like to give a special thank you to all of our TAs, our lead instructors, Ryan Soklaski and Peter Griggs, and our group TA leader, Darshan Krishnaswamy, for the guidance during the course and our final project. And we would also like to shout out Python Like You Mean It and CogWeb.
Citations and links for resources are on the last slide of our presentation. And thanks again for watching.
All right, thank you very much, team. Wow, that was great. So for the last team from the main CogWorks class, we have team Waluigi-Lovers, and I will be playing their video that they pre-recorded.
Hello, everyone. This is team Waluigi-Lovers 2398729. My name is Pranav.
I'm Bhargav.
I'm Nick.
I'm Mindy.
And I'm Ishida. Today, we will be presenting on our final project utilizing the invaluable instruction and mentorship from our instructors and TAs. Each component of our final portfolio involves intersecting CS techniques with music. As music is such an important and fun aspect of all our lives, we thought it would be the perfect field to blend with computers, another fun and important aspect of all our lives. So let the symphony commence. Our first project focused on utilizing a convolutional neural network, a popular type of machine learning model that is extremely good at finding patterns between images, to determine which musical instruments were present in a given audio. Musical pieces from the Hermas dataset compiled by UPF Barcelona were used for analysis. With over 6,000 seconds-long clips, our convolutional neural network was trained to classify audio into 11 different instruments based on the patterns found in the spectrograms, which are a visual method of representing audio files using frequencies. We took inspiration from previous research done in classifying instrument sound with the Hermas dataset by Dominic King and Connor Settle from the Stanford University Department of Computer Science. Though our convolutional neural network structure was similar to theirs, we utilized the Python mygrad library introduced to us by CogWorks, as well as other processing insights from the program for this project.
For our machine learning model, our team chose to use a convolutional neural network. This is a type of neural network that has special layers called convolutions in its structure, where a filter is applied to an input data point that results in some features being activated. The input layer collects input data, which in the case of the convolutional neural network would be pixel information. Hidden layers extract patterns that cannot be observed by humans, aiding in increasingly accurate predictions as the neural network learns from more training data. The output layer returns probabilities for each of the different classifications possible in the model, with the highest probability being its official answer. This network did its best to identify features of our spectrograms, allowing it to learn which graphs correspond to which instruments and give us a prediction based on its learning. After the model trained, the training accuracy came out to be about 95%, while receiving a test accuracy of 75%. This clearly shows signs of overfitting, which is another word for when a model seems to be performing well at training, but actually does poorly at testing. Here's a short clip demoing our model in action.
Along with exploring the different models and tuning hyperparameters further to increase the accuracy, one future extension of this project that can and should be explored is the classification of non-European instruments, so that instrumental music from all over the world is studied and preserved in the form of digital data.
So a critical part of all audio analysis is the Fourier transform, which is a mathematical principle by which any closed function can be perfectly recreated as a sum of sinusoids. We decided to have a little bit of fun with this by taking a graph of the Dow Jones Industrial Average from 1900 to the present day, breaking into chunks, then decomposing these chunks into their most prominent frequencies, and then playing that back through the speakers as a sequence of pure tones. So we can see that in action right here.
Our genre classification project uses a convolutional neural network to analyze a piece of music and output a probability distribution among 9 genres, these being blues, classical, country, disco, hip-hop, metal, pop, reggae, and rock. This project was inspired by Kunal Vidya's article on Towards Data Science regarding his genre classification model. Our 9 genre categories originally came from the Jiqi-Zan dataset, which has been widely used in machine learning projects concerning music genre recognition. The dataset consists of 1,030-second WAV files, each containing a clip of audio corresponding to one of 10 different genres. In both our project and Kunal Vidya's project, from which we took inspiration from, only 9 of the 10 genres were used due to an issue with processing jazz music files. We pre-processed our data by splitting each audio file into 5-second-long clips to increase the size of our dataset and to train our model to be able to recognize genres with shorter clips of audio. After splitting each clip, we generated MEL spectrograms for each audio sample. A MEL spectrogram plots the frequencies at different times of audio samples on a scale that is normalized to how humans perceive sound. Since differences between higher frequencies are more difficult for humans to detect than differences between low frequencies, a MEL spectrogram plots sounds based on a logarithmic scale. MEL spectrograms were saved as NumPy arrays, representing decibel units and stored in respective directories for input for our model. In our project, we used a convolutional neural network.
We had both an implementation of the CNN that used Keras, which was what the Towards Data Science article used, and one that we built with PyTorch. Both models made use of 3 convolutional layers to analyze the image data of each spectrogram, and also a dense layer to have the model output a list of probabilities for how likely the audio fits into each genre. The final version of this project uses the Keras implementation, since our data processing and query functions were originally based around it, but our PyTorch version trains similarly as well as seen in this slide, and the query functions can be easily adapted.
Even though we resulted in a training accuracy of 60% on PyTorch and 70% on Keras, one of the ongoing issues we faced in both of our model versions was overfitting. Essentially, our model was learning specific quirks in the training data that couldn't be generalized to our testing or validation data. And we dealt with this problem partially by reducing our model complexity and the number of layers from 5 to 3. We also created a dropout layer which randomly set input units to 0 with a frequency of 0.3 at each step of training. Both of these changes made positive impacts on overfitting, but if we extended this project further, we would likely look into the dataset's impact on overfitting, as it was made between 2000 and 2001 and may have more narrow or outdated music samples. We trained our model using a batch size of 100 and epoch count of 25, and both of those parameters were calculated through trial and error over time. Now, using a query function, we were able to input audio files and view a corresponding genre probability distribution. Even with overfitting on our model, you'll see that our genre classification program accurately dissects the different styles of music in an audio sample. For example, testing disco, pop, country, and classical songs all returned accurate results. And since we omitted the jazz genre from our project, jazz songs generally had a higher probability of being the blues, since both styles are inherently related. Moving forward, there are definitely some functions to fix and features to add. We would want to experiment more with resolving overfitting and adding audio sampling and song name recognition functions to enhance our genre classification program.
So in another small project, we used an n-gram probability model to generate a sequence of notes based on probabilities generated from data it is analyzed. So this normalized function down here will take in counts of occurrences of notes and use it to associate notes with their probability of occurring, which we can see in this sorted graph down here. Down here, this function is going to act as our trainable model and keep a record of a history of a specified number of notes and keep track of how many times a certain note follows that history in our training data. And then it makes use of the normalize function to associate each history with a list of probabilities for the next note. And now we can just generate a random note, keep track of the history of what's being generated, and use the corresponding probability to select the next note for how many ever notes we want to generate. After trade on a few songs from A minor,
And for our last project, we decided to pay homage to Waluigi, our team mascot, by utilizing Python to transform simple piano pieces into melodies with the Waluigi-Wah sound as the instrument. With the help of the MIT Music 21 library and the Librosa library, we were able to convert MIDI files of simple piano pieces to repeat the same pitches in the wah sound effect. Here are short clips of fur-elise and hot cross buns in the instrument of wah.
So here I'll be quickly showing you what fur-elise in wah sounds like. And here to show the differences in beat length is hot cross buns.
Thank you so much for listening to our presentation. We are grateful to BWSI CogWorks for giving us the opportunity to learn so much about computer science and the chance to apply it in such an amazing way. The course itself gave us such an in-depth knowledge about techniques in many different areas of computer science, and the speakers of the BWSI seminars truly inspired us to keep exploring our passions. Please let us know if you have any questions about our work.
Well, I think we can all give a big wow to that. Am I right? Okay, folks, we are very strapped for time. I'm going to play the final video, which is from the CogWorks team from Mexico.
Good evening. My name is Manny Ulrich Nielsen, and here is my partner.
Hello, my name is Alberto Tamayornet.
And we are the representatives of the high school Prepatec Esmeralda in Mexico. And unfortunately, our partner Diego Perez Rossi couldn't be present here due to COVID complications. Yet we're going to present our CogWorks Autonomous Cognitive Assistance, which we named NUDARPEC, which stands for Neural Ultradynamic Autonomous Role-Playing Polyhedron Entropic Classifier, which is our project, and we would like to present it to you. So firstly, we would like to talk about the data set, which contains more than 16,000 images of dice used for role-playing games such as Dungeons and Dragons or Warhammer. And we decided that our neural network should be able to classify the shapes, the different polyhedrons or figures of these dice. As a project for the future, we could improve it by maybe have the neural network identify the numbers in the dice and sum them up. So my partner, Beto, is going to talk to you more about the data set.
Okay, thank you very much, Manny. Well then, as my classmate Manny said earlier, the data set includes 16,000 images of dice for role-playing games. And well, we decided to reserve 13,000 images for training data, around 2,000 for validation data, and about 1,400 for test data. And then the data is split into 6 categories, which are basically the 6 types of of die, which are D4s, D6s, D8s, D10s, D12s, and D20s.
So, well, now about our pre-processing of the data, we will mention what we did. Firstly, we normalized the data, so the vector operations were much smaller and much faster, also for the training. We also had data augmentation, although this was mostly seen already in the dataset, as the dataset contained images of the dice, but also taken from many different angles, which counts mostly as the data augmentation. And we decided to reduce the dimensions of the images, which were in RGB. We decided to make them grayscale because, well, the color wasn't really as important because we were more focused on identifying the shape, the polyhedron itself. And, well, it was just taking many operations more and much more training effort. So we decided to make it one channel, one dimension, and it would be much faster. So our model is actually pretty simple. It is a sequential model composed of many different convolutional layers. The reason we chose convolutional is because it was very good for identifying images, even if there were some different translations in them, or there were different space variations, even scaling. Actually, all the images in our dataset had different scale and sizes. So we decided to scale them all to images of 100 times 100 pixels. So convolution was the best answer for this. So for our loss function, we chose categorical cross entropy. The reason mainly being that it was much easier to take the labels from the folders, their names, as positions in a vector. So this vector would be much easier and more handable for use in the training. And my partner is going to talk you more about this training we have with our model.
Okay, thank you very much, Manny. So as you can see, our training process consisted of 10 epochs, and we used a batch size of 32, basically to optimize the training process so that it was like efficient and quick, so that we could also have the highest accuracy possible. And well, by the 10th epoch, basically our accuracy for all three sets of data were actually very, very high. For the training data, we obtained an accuracy of 99.99, almost perfect. For the validation data, we got an accuracy of 97.95%. And then for the test data, we got an accuracy of 99.92%. So, well, after making the model, we decided to take our project one step further so that we could use the OpenCV library to be able to capture images with our computer camera, so that we can actually grab the image of a dice that we could show in the camera, and then maybe our model could possibly give us the answer to what kind of dice it was. Unfortunately, based on the type of resolution and the capabilities of our camera, it was really difficult to really get appropriate predictions, and we were getting many errors. Our labels did not the predicted levels didn't really match the true labels. So then we decided to use some samples that we collected from the internet that were completely different to what to the data that we used to train our model.
And so these images my partner was talking about will be used for a demonstration of how our model works and how it predicts labels for images it had never seen before. So here we go. We throw it an image of dice of many sides, and the network should tell us how many sides the dice has. So the first one is 10-sided dice, and the network tells us it is actually a 10-sided die. And well, here we have an 8-sided die and D8. This is another D8, D8. This is a D6. The model says it's a D6. Another D6, D6, D8, another D8. Here we have a D20, 20-sided dice, and the model says it's a 20-sided die, so that's actually pretty good. Here we have another 8-sided die, and it says it's 8-sided, 6-sided, 6-sided, 8-sided, and 8-sided. So actually, it seems that our model has done pretty good with our results right now. It seems to have trained well, and it isn't overfit, so it's actually predicting labels very good for images it had never seen before. So, well, I think that's all we have to show for our model. It's not very complex, but we had a lot of fun doing it. We want to thank you for the space you have given us to make this project and the courses you have given us to learn as much as possible. And well, I don't know if Beto has not anything more to add, but
As well.
for my part, that's everything. Thank you.
Okay, yeah, well, thanks. Yeah, well, pretty much the same. I also want to thank everyone over there at MIT for the courses and the help, also the challenges that they provided, the problems we had to solve. It was very fun. It was very satisfying, see your code run, and then you see the old test pad that passed in the notebook. It was very fun and really challenging. And then the information given was just very clear, very concise. It was just very straight to the point and very clear in general. So, well, thank you very much at the end. And well, I think that's it for me.
Thank you.
Yes, thank you very much. Yes, see you guys.
See you.
Thank you very much. That was an awesome project from the CogWorks team from Mexico. Really cool seeing the dice detector or dice classifier there. That was an awesome application. I'm sure that some of the other CogWorks students would love to play some role-playing games and Dungeons and Dragons with all of you. All right, well, we are all out of time. My TAs and co-instructors have been furiously responding to, sending the CogWorks students your questions from the Slido session and have been responding in Slido. So if you asked a question, please check to see if we've responded. We're sorry that we cannot do a live Q&A session since we're running low on time. But we will have a send-off during the closing ceremony, so this is not farewell quite yet. But everyone give a virtual hand to all of the wonderful work that was done by the Coggies of class of 2021.